Hello friends, welcome to my lecture on partially ordered sets. So, let us begin with the first lecture on partially ordered sets. A binary relation or simply relation from a set A to a set B is a subset of A cross B. So, if you denote the relation by R, then R is a subset of A cross B. Let us say we have an element A belonging to A and B belonging to B, then we write A or B or A not R B, okay, according as A B belongs to R. So, if A B belongs to R, it means that A is related to B, okay, and if A B does not belongs to R, then we say that A is not R related to B. Okay. So, given two elements A in A and B in B, we say that A is related to B or A is not related to B according as A B is in R or A B is not there in R. If R is a relation from A to A, then R is a subset of A cross A and we say that R is a relation on A. Now, let us say R be a relation from A to B, that means R is a subset of A cross B. Then what is the domain of R? The domain of R is the subset of A consisting of the first elements of the ordered pairs of R. Okay. So, in the domain of R, consider all the ordered pairs of R, then their first elements constitute the domain of R, while the range of R is the subset of B consisting of the second elements of all the ordered pairs of R. So, you consider all the ordered pairs of R, then you figure out all the second elements there, okay. They constitute the range of R and obviously, it will be a subset of B. Now, let us say let us define the inverse of the relation R. The inverse of R denoted by R inverse is defined as the relation from B to A, which consists of those ordered pairs which when reversed to R, that is R inverse is B A when A B belongs to R. So, whatever ordered pairs are there, say A B there in R, R inverse will consist of the ordered pairs B A. So, the second element B in R will become the first element in R inverse and the first element A in R will become the second element A in R inverse. Now, let us determine which of the following are relations from A equal to A B C to B equal to 1 2. Okay. So, here R1 is given as A1 A2 C2. Okay. So, you can see R1 is clearly a subset of A cross B. Okay. A cross B is consisting of all the elements say A1, A2, B1, B2, C1, C2. Okay. So, R1 is a subset of A cross B because A1 is there in A cross B, A2 is there in A cross B and C2 is also there in A cross B. So, R1 is a subset of A cross B and therefore, R1 defines a relation in A cross B. Okay. So, this is the relation. Now, let us look at R2. R2 consists of C1, C2 which are there in A cross B, but C3 is not there in A cross B. So, R2 is not a subset of A cross B and therefore, R2 is not a relation in A cross B. So, R2 now R3 equal to empty. The empty set is always a relation because phi R3 equal to phi, R3 is always a subset of A cross B. Okay. Phi is a subset of A cross B. This is empty set. This is called there is always a relation. This always defines a relation in A cross B. It is known as empty relation, okay, known as and when here R 4 is A cross B, the entire set A cross B. So, clearly R 4 is a subset of A cross B. Okay. So, R 4 is a relation in A cross B, and it is called as, because it is the complete set A cross B. So, we call it as universal relation. So, out of these 4, the second one, that is R 2, is not a relation in A cross B, while the others are all relations in A cross B. Now, let us consider this example, let R be a relation on A, okay, 1 2 3, A is 1 2 3, okay. R be a relation on A means R is a subset of A cross A, and it is defined by x less than x is less than y, okay. That is, R is a relation less than, okay. So, write R as a set of ordered pairs. So, let us see, A cross A will consist of elements like 1 1, 1 2, 1 3, 1 4, 2 1, 2 2, 2 3, 2 4, 3 1, 3 2, 3 3, 3 4, 4 1, 4 2, 4 3, and 4 4. Okay. Now, R will consist of those ordered pairs where x is less than y. So, if x by is an element of R, then x should be less than y. So, R is the set of those ordered pairs x by such that x is less than y. So, let us see how many which are the ordered pairs which satisfy that the first element x is less than the second element y. Okay. So, here 1 1 1 2, 1 2 we can take because 1 is less than 2, 1 3 we can take, 1 4 we can take, then we can take 2 3, okay, because 2 is less than 3, then we can take 2 4, we can take then 3 4, okay. Then yeah. So, R is equal to the set of ordered pairs 1 2, 1 3, 1 4, 2 3, and then 2 4, and then 3 4, okay. Because in all these ordered pairs the x, that is first element, is less than the by second element. In all others this condition does not hold good. Okay. Now, so now write R as a set of ordered pairs. Also find the inverse R inverse of the relation R. So, R inverse is equal to, if x by belongs to R, then y x belongs to R inverse. So, we have y x, okay, where x by belongs to R. So, this will consist of 1 2 will become 2 1, 1 3 will become 3 1, 1 4 becomes 4 1, 2 3 becomes 3 2, 2 4 becomes 4 2, and 3 4 becomes 4 3. So, here the first element, okay, is by, and by is then greater than x, it is greater than the second element. So, this is how we find the inverse of R. Now, let us define partially ordered set. Suppose R is a relation on a set S which satisfies the following 3 properties. First property is reflexive, A is related to A, that is A belongs to R, okay, that is the first property for every A belong to S. Antisymmetric, if A related to R, that is AB belongs to R and BA belongs to R, that will happen only when A is equal to B. So, if relation is symmetric, then if A are B and B are A, okay, both hold, A is related to B and B is related to A, then A must be equal to B. Now, the third property, transitive, if A is related to B and B is related to C, then A is related to C. That means, if AB belongs to R and BC belongs to R, then AC also belongs to R. We shall then call R to be a partial order, R an order relation, and S together with the partial order relation will be then called partially ordered set, or we call it as an ordered set, or in brief we call it as a poset. Poset means partially ordered set. Now, let us define the usual order, okay, on the set of positive integers. On the set of positive integers, and the usual order is the relation less than or equal to, okay, which is also there on any subset of the set of real numbers. A partial order relation is usually denoted by this symbol, okay, this symbol. And what is the meaning of this symbol? If this symbol is there between A and B, we say that A precedes B, okay, A precedes B. If we have this symbol, okay, where this one is not there, okay, then we say that A strictly precedes B. Now, A strictly precedes B means A precedes B, but A is not equal to B, okay. Now, if we have this symbol, okay, this means that A succeeds B if B precedes A, okay. You can see B, this symbol means precedes. So, if B precedes A, then A succeeds B. Now, if this symbol is there, we say that A strictly succeeds B, okay, if B strictly precedes A. So, we shall make use of these symbols on a partially ordered set. Now, consider PS as the power set. Let us consider the power set of the set of that is the set of all subsets of a given set S, so that the inclusion relation is a partial ordering on the power set S, okay. So, first thing that we have to see is reflexive. Reflexive means A is related to A for all A belonging to S. This is the first thing we have to see. So, let us take a set in PS, okay, let A belongs to PS, the power set of S, okay. Then A is related to A because A is contained in A, okay. This is always true. Relation here is this inclusion relation. So, A is always contained in A. So, we say that A is related to A. So, this reflexive property holds. Then antisymmetric. So, let A is B are related to B and B are related to A, okay. Then we have to show that A is equal to B. Now, A or B means A is contained in B, okay, and B is related to R means B is related to A means B is contained in A, okay. So, A contained in B and B contained in A implies that A is equal to B. If A is a subset of B and B is a subset of A, then they must be equal. So, A is equal to B, and so therefore, if A is related to B by inclusion relation and B is related to A by the inclusion relation, then A must be equal to B. So, antisymmetric property holds, and the third one is transitive property. So, if A is related to B and B is related to C, okay, then we have to show A is related to C, okay. So, A is related to B implies that A is contained in B and B is related to C means B is contained in C, okay. Now, A is contained in B and B is contained in C. implies that A is contained in C. So, which means that A is related to C. Okay. So, the transitive property also holds, and therefore, the relation inclusion relation is a partial ordering on the power set S of the given set S. Now, let us show that the relation greater than or equal to is a partial ordering on the set of integers Z. Okay. So, first we prove that reflexive property. Take any A belonging to Z, let A be any integer, okay. Then we know A is always greater than or equal to A, okay. And so, A is R related to A, okay. Then reflexive, after that reflexive we go to antisymmetric. So, let us say A is R related to B and B is R related to A, okay. A B belong to Z, okay. Then A is R related to B implies A is greater than or equal to B, and B R related to A implies B is greater than or equal to A, okay. So, this means what? So, A greater than or equal to B and B greater than or equal to A together can hold, okay, only when they are equal, because this also I can write as B greater than or equal to A means A less than or equal to B and B less than or equal to A, okay. So, A less than or equal to B less than or equal to A implies A is equal to B, okay. Now, then we go to transitive. So, let us say A is R related to B and B is R related to C, okay. Then we have to prove that A is R related to C. So, A is R related to B implies A is greater than or equal to B and B is R related to C implies B is greater than or equal to C. Now, A is greater than or equal to B and B greater than or equal to C implies that A is greater than or equal to C. So, this means that the relation greater than or equal to is a partial ordering on the set of integers Z. Now, consider the set of positive integers n, the set of natural numbers n, then the divisibility is a partial ordering on the set n. Let us prove that. So, reflexive okay. So, let A belong to n, A belong to n, A be an integer, positive integer, then A divides A, we know A divides A, okay. Hence, A is related to A, okay. So, this is valid for any A belonging to n. Then antisymmetric, let A be related to B and B be related to A. A be related A are B and B are A, okay. Then A R B implies A divides B, which means that B equal to K1 into A for some positive integer K. For some positive integer K1, okay. B is R related to A implies B divides A, okay, which implies that A is K2 times B for some K2 belonging to n, for some positive integer K2 belonging to n. Now, from here what we can see, from this equation and this equation we find that B is equal to K1 into A. A we can put as K2B. So, B equal to K1 K2B, okay. Now, B is a positive integer. So, we can divide by b. So, this implies 1 equal to k1 k2. Now, k1 k2 are both positive integers and their product is 1. It means that k1 is equal to k2 equal to 1. Okay. So, what we will get, k1 and k2 both are equal to 1. So, we will get b equal to a equal to b. That means, we have, so transitive, so antisymmetric property holds. Now, next we go to transitive property. Okay. So, let us say A B are related to B, B B are related to C, okay. B B are related to C, then A divides B and B divides C. Okay. A divides B implies B equal to k1A for some k1 belonging to n. Okay. And B divides C implies C is equal to k2B for some k2 belonging to n. Okay. So, what do we get? A divides B gives B equal to k1A and B divides C gives C is equal to k2B. Okay. So, let us replace the value of B equal to k1A in the equation C equal to k2B. So, C equal to k2B gives C equal to k2 into k1 into A. Okay. k1 k2 are positive integers. So, k1 into k2 is also a positive integer. So, this means that A divides C as k1 k2 belongs to n. Okay. So, the when we consider the set of positive integers n, then divisibility is a partial ordering on the set n. Now, let us go to this symbol which we talked about earlier. This means when this symbol is there between A and B, okay, we say that A precedes B. Okay. So, let this be a partial ordering of a set S, then the relation this, okay. This relation means succeeds. Okay. When it is there between A and B, it will mean that A succeeds B. Okay. So, we have to show that this relation is also a partial ordering of S. It is called the dual order. Okay. So, let us see, we have to show that this is a first we show the reflexive property. Reflexive property means we have to show that let A belong to S. Let A belong to S, then A is R related to A is related to A. This means we have to prove that is this. Okay. Now, this is also this is already a partial ordering of the set S. That means A succeeds, sorry, A precedes A. This is given, this is already there. That is A precedes A. Okay. This is a partial ordering on the set A. So, with respect to this partial ordering, S is reflexive. This is a reflexive relation on S. So, this means A precedes A is always there. When A precedes A, then this A succeeds this A. Okay. So, A succeeds A. Okay. So, A is related to A, and then let us prove the antisymmetric. And antisymmetric, let us say let A be related to B and B be related to A. Okay. Then we have to show that A and B are equal. So, A is related to B means A succeeds B and B succeeds A. Okay. A succeeds B and B succeeds A. Now, A succeeds B means B precedes A, okay, and B succeeds A implies A precedes B. Okay. Now, so that what we have, A precedes B and B precedes A. Okay. Then by the fact that this partial ordering is transitive. Okay. So, A precedes B means A precedes B and B precedes A. Okay. Now, this is a partial ordering on the set. So, with respect to this partial ordering, we have antisymmetric property, and this that implies that A is equal to B. Okay. Because this is nothing but the anti-symmetric case for this partial ordering. Okay. Now, the third one, transitive. So, let us say A be related to B and B be related to C. Okay. Then A or B implies A succeeds B, okay, and B related to C implies B succeeds C. Now, A succeeds B means B precedes A, okay, and B succeeds C means C precedes B. Okay. So, now C precedes B and C precedes B and B precedes A, okay, and this is a partial ordering of the set S. Therefore, with this partial ordering, this partial ordering is transitive. So, C is precedes B and B precedes A implies C precedes A, okay, or which is same as A succeeds C. Okay. A succeeds C, that means A is related to C. Okay. So, that is how we show that this notation, okay, which is the notation that A succeeds B is also a partial ordering of S, and it is then therefore called it is called dual order. Okay. Now, A succeeds B if and only if B succeeds A. If A succeeds B if and only if B precedes A. Okay. Hence, this notation, okay, which is the notation for A succeeds B. So, this notation is the inverse of the notation A precedes B. Okay. This is the notation for A precedes B and this is notation for A succeeds B. So, this is inverse of this relation, and we should show it by writing this notation which for A precedes B is equal to A succeeds B inverse, this notation, inverse of this notation. Now, describe the dual order of the following relations, set inclusion. Okay. So, let us go to set inclusion first. Okay. So, this we want to know what is the inverse of this. Okay. So, inverse of this means let us say this is the notation, this same as this. Okay. So, A precedes B, okay, means that A is subset of B. Okay. So, the inverse of this will be then the inverse of the inverse is B contains A. Okay. So, when you write the inverse of A in contained in B, what you get is B contains A. Okay. So, the this is the notation for set inclusion, this is notation for set containment. So, B contains A. So, this notation is the inverse of this. Now, the next case was divisibility on n. Okay. So, let us see what is the inverse of divisibility on n. So, divisibility, so let say let A B belong to n, then this notation, okay, is division. Okay. So, A means that A divides B. Okay. A divides means A divides B. Okay. That means we can say inverse will be, the inverse will be B is a multiple of A. Okay. When A divides B, its inverse is B is a multiple of A. Okay. Now, we go to this definition. So, let A be a poset. Okay. This is the order relation on A, and B is subset of A. It is not necessary that it is less than or equal to, it is some relation on A. So, let this be a poset and B be a subset of A, then B is called the poset induced by A if x less than or equal to by, if and only if x precedes by. Okay. So, suppose A is a partially ordered set, it is a poset with the partial order relation given by this notation, okay, and B is any subset of A, then B will be called a poset, okay, induced by A if x less than or equal to y. You take any two elements x by belonging to B, okay, then x less than or equal to y, okay, as because this is relation in A. So, x less than or equal to y in A if and only if x precedes by, okay, in B. Okay. So, that should hold. So, the subset B with the induced order is called an ordered subset of A. Now, let us look at an example on this. Suppose n is ordered by divisibility. Okay. N is ordered by divisibility. Determine whether or not A is an ordered subset of n, where A is consisting of 2, 3, 4, 5, 6 with the usual order. Usual order means less than or equal to. Okay. Usual order, as we have seen earlier, it means less than or equal to. Now, you can see A will be the set induced by S, induced by n, provided A will be called this poset induced by n whenever you take any two elements in A. Okay. We have A less than or equal to B if and only if A precedes by, n less than or equal to is the notation for the partial order in the set A. So, what we have here? We can see that 2, 3, okay, 2, let us take 2, 3 belonging to A, okay, then 2 is less than or equal to 3, okay, 2 is less than or equal to 3, but 2 does not divide 3. Okay. In n, the n is partially the partial order relation in n is divisibility. Okay. So, we have taken x to be 2, y to be 3, okay, and then we see that with respect to the usual order in A, okay, 2 and 3 are related, 2 is less than or equal to 3, but 2 is not 2 does not divide 3. So, this condition does not hold. This one, x precedes by, we should have x precedes by if and only if x less than or equal to y. This is the order relation in the subset, and this is the order relation in the set given set. So, here the order relation in n is divisibility. Okay. So, this holds, but this does not hold, and therefore, A is not an ordered subset of n. Okay. So, this should happen for any two elements in A, okay. But we find two elements in A 2, 3 for which 2 is less than or equal to 3, but 2 does not divide 3. So, this is not a not an ordered set, not an ordered subset of n. Okay. Now, let us look at the second part, A equal to 2, 4, 8, 2. Okay. So, what you do, suppose I take any two elements here, say 2 4, or you can take 4 8, or you can take 2 8, okay, or you can take 8 32, or you can take 4 32 or 2 32, then x is less than or equal to by. Okay. So, let us take 2 and 8, okay, in A, then 2 is less than or equal to 8, and also 2 divides 8. Okay. So, this is valid. Okay. 2 divides this if and only if this condition is valid there. Take any two elements. Okay. If x is in A, we are taking the usual notation, yeah, usual order. So, x is less than or equal to y if and only if x divides by. So, this holds true in the case B. So, A is an ordered subset of y. Ordered subset of n, sorry, ordered subset of n. Now, we go to comparability. The elements A and B are called comparable if one of them precedes the other, that is A is precedes B or B precedes A. Okay. Thus, A and B are non-comparable if neither A is precedes B nor B precedes A. For example, suppose n is ordered by divisibility, okay, then 27 and n are comparable because 7 divides 21, but 3 and 5 are non-comparable because neither 3 divides 5 nor 5 divides 3. Linearly ordered set. An ordered set S is called linearly or totally ordered, okay, and S is called a chain if every pair of elements in S are comparable. Okay. So, if you take a set S, okay, then you take any pair of elements in S, if they are comparable, that is A precedes B or B precedes A happens, then we say that S is totally ordered or linearly ordered, and the set S will be called as Hn. For example, the positive integer set of positive integers, okay, the set of positive integers with the usual order less than or equal to linearly ordered. If you take any two elements in x by in n, then either x is less than or equal to by or by is less than or equal to x. So, it is all with the usual order, the set of positive integers is a linearly ordered or totally ordered set. Now, suppose n is ordered by divisibility, okay, then we have to see whether the following subsets of n are linearly or totally ordered. Okay. So, let us look at the set A consisting of a single element 7. It consists of a single element 7. So, it is totally ordered because there is only one element. So, when you take a pair of elements, it will be 7 7. So, 7 divides 7. So, it is a linearly or totally ordered set. Now, here let us see 2 4 8 32. Okay. You take any two elements in this, okay, 2 4 or 4 2, okay, then or you take 4 8 or 8 4, okay, 8 32, then either 4 divides 8 or 8 will divide. If you take 4 8, then 4 divides 8. If you take 8 32, then 8 divides 32. If you take 2 32, 2 divides 32. So, if you take any pair of elements in A here in part B, then one divides the other. Okay. Now, here in the case of 15 5 32, again if we take a pair, okay, then we find either the pair will be 15 5 or 5 30 or 15 30. There is always the situation that one element divides the other element. So, this set and this set and this set are totally ordered or linearly ordered. If you take the entire set n, okay, entire set n, okay, then this n is not, this set is not linearly or totally ordered, because if you take 1 2, okay, if you take 1 2, then if you take say 2 3, if you take 2 3, okay, in this set, let me call this set A, as of course, this A is equal to n. So, 2 3 you take in n, there neither 2 divides 3 nor 3 divides 2. So, this A is not linearly or totally ordered. If you take 3 15 5, okay, 3 15 5, this is also not linearly or totally ordered, because when we take 3 5, okay, then neither 3 divides 5 nor 5 divides 3. So, this set and this set are not totally or linearly ordered. Okay. So, that is all in this lecture. Thank you very much for your attention.